We're doing problem 5. So first, we're gonna run through the quicksort algorithm. So we take in a list, and this list will have a length n. So if the length is less than or equal to 1, then we just return it as it is. Or else we pick an element in our list, then we find the number of elements less than it, and the number of elements that are less than or equal to it. Then by doing this, we can rearrange it so that we have a section less than x, equal to x, and greater than x. Then we run quicksort on two of those sections.
So to prove the correctness of this algorithm, we can use induction on n, where n is the length of the list. So let the inductive hypothesis be this statement that the quicksort algorithm correctly sorts all lists of length greater than or equal to 1 and less than or equal to n in ascending order. Then the base case is where n is equal to 1. In this case, we have a list of one element, which is obviously already sorted in ascending order. And in the algorithm, we see that we simply return in this case. And this is correct because a list of one element is already sorted. So the base case holds. And now we need to do the inductive step. So assume that the inductive hypothesis is true for some positive integer n, which means that the quicksort algorithm correctly sorts all lists of length k, where k is greater than 1 and less than or equal to n in ascending order. So now we consider a list of length n plus 1. Since n plus 1 is greater than 1, the quicksort algorithm will choose a random element x from the list in line 6. And we define C to be the number of elements less than x and D to be the number of elements less than or equal to x in this list. And the list is reordered such that all numbers less than x are moved to the left of numbers equal to x. And the remaining numbers, which are all greater than x, are to the right of numbers less than or equal to x. So this means that clearly the sublist from index c plus 1 to d is sorted because every number in this sublist is equal to x. And all elements in the sublist from index 1 to c are less than x, and all elements in the sublist from index d plus 1 to n are greater than x, which means that if we sort these two sublists correctly, then the entire list from index 1 to n will be sorted. And by our assumption, the quicksort algorithm correctly sorts the sublist from index 1 to c and the sublist from d plus 1 to n in ascending order, because the length of these two sublists is less than or equal to n. So therefore, calling quicksort on these two sublists in lines 10 and 11 sorts the entire list of elements index 1 to n in ascending order. And this completes the proof.